All right, we're about to look at something that on the surface seems almost too simple, just a triangle made of numbers. But what if I told you this little pattern is basically a key that unlocks some of the deepest and coolest secrets in all of mathematics? Stick around because you're about to see just how deep this rabbit hole really goes.
So what if a simple little adding game, something you could literally teach a kid in about 30 seconds,
Was actually a secret map for solving complicated algebra, for creating these mind-bendingly beautiful fractals, and even hiding one of the most famous number sequences in history? I know, it sounds kind of nuts, but it's absolutely true. So let's dive in and see how it works.
Okay, first things first, let's just build this thing. The real beauty of Pascal's triangle is that it starts with the simplest rules imaginable. People call it a childlike adding game, and you're about to see why.
It all kicks off with a single number 1 right at the very top. From there, you just put ones all the way down the sides. And for the numbers in the middle, well, you just add the 2 numbers that are right above it. So 1 plus 1 gives you 2. On the next row down, 1 plus 2 is 3, and 2 plus 1 is, well, also 3. You just keep this exact pattern going, and you can make the triangle as big as you want. See? Simple, right?
So it's a neat pattern, but why? What was this actually for? Well, its main job, its original purpose, was to be a massive shortcut for a type of algebra problem that, let's be honest, most of us didn't exactly love in school: expanding binomials.
Remember trying to solve something like x minus 2 cubed? The long way, which you can see over on the left, is just, it's a mess. It's tedious, there are a million places to make a small mistake. But now, look over at the right. Using Pascal's triangle, you just grab the numbers from the third row, 1, 3, 3, 1. You use those as your multipliers and bam, you get the exact same answer in like 1/10 of the time. This is really our first big clue that this triangle is way more powerful than it looks.
But here's the thing. Those numbers aren't just random helpers for your old algebra homework. No, they have a much, much deeper identity in the world of math, and it all has to do with probability and choices. And this brings us to this idea called combinations. It's really just a fancy way of asking, how many ways can I choose stuff? For example, if you have a group of 4 friends, how many different 2-person teams can you possibly make? The formula for this, n choose r, is designed to answer exactly that question.
So here's where it gets amazing. Every single number in Pascal's triangle is actually the answer to one of these combinations problems. So if we want to know, say, how many ways you can choose 3 things from a group of 6, we can plug it into the formula, do the math, and the answer is 20. And guess what? If you go to row 6 of the triangle and count in 3 spots, the number is 20. The triangle isn't just a pattern, it's a complete, perfect map of combinations.
Okay, so its main job is pretty cool, but that's just the beginning. This is where things get really wild. Let's start peeling back some of the layers and see what other secrets are hiding in plain sight.
So the first secret is super simple, but so elegant. If you just add up all the numbers in any given row, you always get a power of 2. Row 1 adds up to 2, which is 2 to the power of 1. Row 4 adds up to 16, which is 2 to the power of 4. It just works, every single time, no matter how far down you go.
Okay, that was neat. Let's try another trick. What if, instead of adding the numbers, we just read them off like they're a single big number? Well, the first few rows give us 1, then 11, 121, 1,331. Wait a minute, those are the powers of 11. That's incredible. But then, we get to row 5 and it has double-digit numbers. Suddenly, the pattern looks totally broken.
So is that it? Was this beautiful pattern just a fun little coincidence that fell apart after a few steps?
No way! The pattern isn't broken, it's just hiding. You just have to treat it like you're doing addition in elementary school and carry the 1. So if you look at that row, the 10 on the right gives its 1 to the 5 next door, which makes it a 6. The next 10 does the same thing. And once you do all the carrying, you get 161,051, which is exactly 11 to the power of 5. The pattern was there all along.
All right, let's switch things up again. We've been looking at the rows horizontally. What happens if we stop doing that and we start summing up the numbers along these sort of shallow diagonals?
Let's give it a shot. The first sum is just 1. The next one is also 1. The next one is 2. Then 3. Then 5. Then 8. Hold on a second. 1, 1, 2, 3, 5, 8.
Does that sound familiar? It should. It's the Fibonacci sequence, one of the most famous patterns in all of nature and math, just hanging out there in the diagonals.
Okay, for this last secret, we're going to do something that seems totally random. We're going to forget the actual numbers for a minute. Instead, we're just going to ask a simple question. Is the number odd or is it even? And if it's odd, we'll color it in, and if it's even, we'll just leave it blank.
So when we apply this super simple odd-even rule, something incredible starts to happen. As you go down the triangle, you start to see these big, empty triangles made of even numbers just appearing out of nowhere. Now, if you kind of zoom out and look at the whole shape that's forming, what does that remind you of?
Well, this pattern of odds and evens turns out to be a perfect visual match for a really famous fractal called Sierpinski's triangle. Just by asking if a number is odd or even, we've turned our simple number triangle into this complex, infinitely repeating geometric shape. I mean, that is just a mind-blowing connection between basic arithmetic and the world of fractals.
So let's just recap for a second. We started with a simple adding game, and from that, we found shortcuts for algebra, we found the powers of 2 and 11, we found the Fibonacci sequence, and we found a direct link to the geometry of fractals. All of that just from adding two numbers together.
And the craziest part? We've only just scratched the surface. As one mathematician put it, this is an infinite triangle. Who knows what other crazy patterns are waiting to be discovered on the 1,000th row or the 1,000,000th? We just have to keep looking. The exploration never, ever ends.
It started with something as simple as 1 plus 1, and it ended with connections to infinity. It really just leaves you with this one last, fascinating question. How many other simple patterns are out there in the world, just waiting for us to look at them in the right way to reveal the entire universes they're hiding inside?